In this lesson, we are going to talk about cell potential. The chemical changes that take place in galvanic or electrochemical cells are accompanied by changes in potential energy. Electrons spontaneously flow from a position of higher potential energy at the anode to a position of lower potential energy at the cathode. The moving electrons can do work, such as lighting a bulb or turning a motor. The difference between the potential energy at the anode and the potential energy at the cathode is called electric potential, which is denoted by the capital E of a cell. The unit used to measure the electric potential is called the volt, with the symbol capital V. So if we were to write that, we would say that, for instance, potential energy is equal to 1 volt. Electric potential is now more commonly known as cell voltage. It could also be called cell potential. So note that when we're asking questions, I can either use electric potential, cell voltage, or cell potential. Cell potential is measured using a device called a voltmeter. A cell potential is the difference between the potentials of two half cells. However, you cannot measure the potential of only one half cell because a single half reaction cannot occur alone. That means we can't just have oxidation happening. If it's losing electrons, what's gaining it? Or we can't just have reduction happening because if it's gaining electrons, where are these electrons coming from? The cell voltages are combinations of voltages for each half cell called half cell voltages. The half cell voltages can be obtained by connecting each half cell to a standard half cell, which was decided upon to be the hydrogen half cell. That means that someone decided to use the hydrogen half cell and arbitrarily assign it a voltage of 0 volts, and then connecting all of the other half reactions to this hydrogen cell and recording the difference in the voltmeter. If the voltage of many half cells are measured, they can be listed from positive to most negative in what's called a table of standard half cell potentials. This is just a very small glimpse of all of the different voltages for the half reactions, and this is actually in your data booklet. Since this is in your data booklet, this will be given to you for your test as well as your public exam, and we're going to be using this a lot throughout this section, so you might want to have that handy. There are some things that you should know about the table of standard reductions. One, it's called the table of standard reductions because each half cell is written as reduction. That's really, really important. The half cell potential for a reduction half reaction is called the reduction potential. If you actually have a look at the list, you will notice that the most easily reduced molecules and ions are near the top of the list, and the least easily reduced molecules and ions are at the bottom of the list. So the table of standard reductions is given as the highest reduction at the top and the least likely to undergo reduction at the bottom. If you want to know what the potential will be if this is written as oxidation, it means that you would need to flip the half reaction, and therefore you would flip the sign on the potential. The numerical values of cell potentials and half cell potentials depend on various conditions. So the table of standard reduction potentials is true when ions and molecules are in their standard states. Aqueous ions and molecules have a standard concentration of 1 mole per liter. Gases have a standard pressure of 101.3 kilopascals or 1 atmosphere. The standard temperature is 25 degrees Celsius or 298 Kelvin. Standard reduction potentials are designated by the symbol E degree sign, where the degree sign indicates that this is under standard state. The formula that we'll be using in this section to calculate the cell potential is given as potential of the cell is equal to the standard potential of the reduction half reaction plus the standard reduction of the oxidation half reaction. Remember, however, that the table is given as reduction. So you would need to flip the reaction and the sign before you actually plugged it into this equation. Let's go through this first example. Calculate the standard cell potential for the galvanic cell in which the following reaction occurs. First, we ask ourselves what is required. Well, we need to find the standard cell potential for the given reaction. So let's plan out our strategy, and these are the steps that you can use no matter what question is asked to you in the future. Step number 1, the first thing you need to do is to write out the oxidation and the reduction half reactions. Well, we've been practicing that in this unit. So the first thing we have to do is break them apart according to their elements. We have 2I negative, and note this is written on the next page, so you should just pay attention. Goes to I2 solid, and we have Br2 liquid, goes to 2Br negative aqueous. And of course, since we're writing out half reactions, these need to include the electrons. Notice that we have a 2 negative charge here on the reactant side. We have an overall charge of 0 on the product side. We always add electrons to the higher number, which would be 0, and we would need to add 2 of those. In the second half reaction, I have an overall charge of 0 on the reactant side, 2 negative on the product side, so we're going to apply the same logic in this one. So we've now written out the half reactions. The other thing that we need to do once we've written out the half reactions is to identify which one is undergoing oxidation and which one is undergoing reduction, keeping in mind oil rig. The first one here is losing electrons, so this one is the oxidation. So iodine is undergoing oxidation, and the bromine is undergoing reduction. Step number 2 to answer this question is to locate the relevant reduction potentials in the table of standard reduction potentials. This is your standard reduction potential of half cells table, which is in your data booklet and given for an exam and test situation. So in step number 1, we wrote out the 2 half reactions. What you need to do now is to find those half reactions in this list. Note that in any situation, you would only need to find the half reaction. You do not need to worry about if the coefficients are all the same. For instance, we wrote a half reaction, Br2 plus 2 electrons goes to 2Br negative. If you had a situation where that was 4Br2 plus 8 electrons goes to 8Br negative, that would be fine. You would still find the same half reaction. So I noticed that here I have Br2 plus 2 electrons goes to 2Br negative. And we continue down the list and we find the one for iodine as well. So you need to identify this on your list, putting your finger by it, putting a pencil mark, and then erasing it. You don't want to write this up too much because you're going to be using this over and over and over again. After you found both half reactions in the table, you must remember that they're both written as reduction. So you need to go back to step number 1 and see which one you identified as undergoing oxidation so that you can flip the equation as well as the sign that's associated with it. Recall from step number 1 that we identified iodine as undergoing oxidation. So at this time, we'll change the equation to make sure that it's actually undergoing oxidation like we did in step 1. We won't write it the way that it's written from the table. As well, we will write down now the cell potentials from the table next to the half reactions, making sure that we change the sign there on the one that's undergoing oxidation. Once you've changed the sign, the last step that you would have to do is completing the equation by just adding these two together. Once they're added together, we will get an overall answer of 0.530 volts. Let's go through our own example. Calculate the standard cell potential for the galvanic cell in which the following reaction occurs. Step number 1 is to write out the half reactions. So again, we're going to split them up according to the element. We have CD2 positive goes to CD solid, and we have Cr solid goes to Cr2 positive. Since we're writing out the half reactions, we must also include the number of electrons. Here we would need 2 electrons, 2 and negative 2 makes 0, and we would need 2 electrons here. Hopefully at this stage in the chapter this comes very easily for you. If it's not coming so easily and you're questioning where I got these numbers, please see me for some additional help. The last thing we need to do here in step number 1 is we need to identify what's undergoing reduction and what's undergoing oxidation. Again, remembering oil rig. The first half reaction, we are gaining electrons, so this one's undergoing reduction. Therefore, we're going to find this as is in the list, and we're going to take the cell potential from the list as is. The second half reaction is losing electrons, so this one is undergoing oxidation. Therefore, when we find this in the list, we need to flip the sign with the cell potential. So let's go ahead and find this in the list now. Looking down through the list for the two half reactions that we have identified, I can see CD half reaction there, and the chromium half reaction I see down here. Be very, very careful that you're identifying the exact half reaction. For instance, some people may have identified the one next to it, but notice that is not the same half reaction that we've written from step number 1. We are now going to take these cell potentials and rewrite them in for our half reactions. Putting all these steps together now, let me rewrite out the half reactions. 2 electrons plus CD2 positive goes to CD solid. Cr solid goes to Cr2 positive plus 2 electrons. We identified the first one as reduction. We identified the second one as oxidation. The reduction one stays the same, so we'll write that out. E naught for reduction is equal to negative 0.40 volts. The E naught for oxidation, we have to change the sign from the list, so we're going to call that positive 0.91 volts. And then we're going to add these two together on our calculators, or in our heads if we're good enough. E cell, therefore, is equal to 0.51 volts. The last thing we need to cover in this section is if something is spontaneous as written. And this could be either a follow-up question to finding the cell potential, or it could be a question on its own. If it is a question on its own, however, you must first find the cell potential in order to answer the question. The reason for that is because of the following. A spontaneous reaction only occurs when the oxidizing agent is above the reducing agent in the table of reduction potentials, so you can find it if this is a multiple choice question. However, if it is a long answer question, you do need to mathematically prove it. Therefore, you have to find the measured cell potential. If it has an overall positive value, then we say it is spontaneous. If the overall answer is negative, it is not spontaneous. So if we look at the first example that's shown, we've been asked if the reaction that's given is spontaneous as written. Therefore, they broke it up into their two half reactions where hydrogen is undergoing reduction and copper is undergoing oxidation. They found them in the list and added them together and got an overall negative 0.34. Therefore, it is not spontaneous. We can go through our own example from the beginning right to the end in order to find out if this one is spontaneous. So first we would write out the half reactions. Zn solid goes to Zn2 positive plus 2 electrons, and Cr3 positive aqueous goes to Cr2 positive aqueous, and therefore we would need to add an electron there. Notice that we do not need to write the overall reaction, therefore it does not matter that the total number of electrons lost does not equal the total number of electrons gained, because again, we don't need to write the overall. We do, however, need to identify if they're oxidation or reduction. The first one involves a loss of electrons, so that one's undergoing oxidation. The first one is gaining electrons, so this is undergoing reduction. That means when I find the chromium half reaction in the table, I'm going to leave it as is, but when I find the zinc one, I'm going to have to flip the sign. So I encourage you now to go and try and find the half reactions in the cell potential table. You would find chromium as is, because that's the one that's undergoing reduction. and therefore it has a cell potential of negative 0.41 volts. Zinc you would have to find in the standard cell potential table, but you would have to change the sign to positive 0.76 volts. When we add that together, we get an overall cell potential of 0.35 volts. Therefore, this one would be spontaneous. I do want to bring a couple of things to your attention in this example. One, in previous years, in fact last year, this question was marked for significant figures. So this one, we're adding or subtracting. Well, technically we're adding. And the rules for adding state that the answer has to have the least number of decimal places as the two numbers that you are actually adding together. So it's not significant figures, it's the number of decimal places. So in this case, if we were adding two numbers together, which on our calculator gave us something like 0.20, your calculator would only show you 0.2. And you'll need to have the state of mind to realize that that's not the correct number of significant figures and quote an answer 0.20. So you need to remember to add in that 0. This question was also marked for units, so don't forget that the oxidation and reduction half reactions are measured in volts, and therefore the overall answer is measured in volts. Don't forget the units there as well. The other thing you may notice is that the total number of electrons gained do not equal the total number of electrons lost, and therefore there was no manipulation taking place here. The overall cell potential, as well as the half reaction potentials, it does not matter about the quantity of electrons that are there. So for instance, we would not take the cell potential for reduction, and since the number, we only have one electron, we do not need to multiply this by 2. It's just the number from the table, irregardless of the number of electrons that are being lost or gained. At this time, you now have enough information to start working on electrochemistry worksheet number 5.